This is an example of something on fourth night homework. We have a water depth that's initially 100 centimeters. And we have a rule for how quickly water flows out of this container, or at least how quickly the depth of water changes in this container. When the depth in centimeters is y, the depth changes at a rate of y prime equals negative 0.15 square root of y. And that's in centimeters per second. So you put the numerical value of the depth in centimeters in here, do the calculation, and you get y prime, which is the rate in centimeters per second at which the depth changes. Okay, so if the depth is 100 centimeters, what is y prime? You should do that before you look ahead. You should be able to do that in your head very easily. Okay, well, you should have paused and done that. In any case, y prime is then what? If the depth is 100 centimeters, we put 100 in here. So we get negative 0.15 times 100 equals what? Negative 0.15 times 10, because the square root of 100 is 10, which is negative 1.5, and that means negative 1.5 centimeters per second. Now, next question. At this rate, how much will the depth change in 10 seconds? And what will be the new depth? Okay, well, you should do that. Now, you can pretty much do it in your head. If you got to jot down a few numbers, you can, but this is not something that gives anybody trouble. Okay, well, to answer this, we multiply the negative 1.5 centimeters per second, which tells us how many centimeters this depth changes in every second, by our 10 seconds, and we get negative 15 centimeters. So the depth is going to be 100 centimeters minus 15 centimeters, or 85 centimeters. It should all make sense. Now, the one thing that might not make sense is that we know that as the depth drops to 85 centimeters, the rate at which water flows out, which depends on the depth, is going to change. So y drops from 100 down to 85. This rate is going to drop from about 1.5 centimeters per second to something that I think I calculated as 1.39 centimeters per second. So we haven't accounted for that, so we're kind of overestimating how much the water is going to drop. We're using the rate that was there when the depth was 100 centimeters and applying it all the way down to 85 centimeters. We could kind of correct that. We could calculate the rate that you get at 85 centimeters, average it with the rate at 100 centimeters, and then recalculate how far it'll drop. But we're not going to do that. That's kind of what we call a predictor-corrector type method, and that gives you much improved accuracy. It's not perfect. So if you want to do that sort of thing, if you need much better results, you can get them using that sort of strategy, and even strategies that build on that. That would be a linear average of the two, and you do a quadratic average, you get this Simpson's rule thing. Okay, well, that's all stuff that we don't have to worry about. We're just trying to get this basic idea. So the basic idea is we use this rule to approximate how much the depth is going to change and to get the new depth. Okay, well, the water is going to continue going after 85 centimeters unless we plug the hole or something happens. So the question is now, what is the value of y prime? Well, we're going to plug 85 in here and we're going to do the calculation. I think we get about negative 1.39, so the rate is about negative 1.39 centimeters per second. So that in 10 seconds, delta y is going to be what? Well, it's going to be about negative 13.9 centimeters. Put that together with your 85 centimeters, you find that you're at 71.1 centimeters. Well, clearly, we can then take this and plug it into our formula for y prime and predict the next 10 seconds. Again, we're overestimating the rate of drop, but depending on your application and for the precision you need, we're probably not overestimating it too awful seriously. We then can sketch a graph of our depth versus clock time. It's clear that that graph is going to be concave upward. Why? because the rate here is decreasing. We fall by less during the second interval than we did during the first, and we can see that we're going to fall by less in the third interval than in the second because the depth keeps decreasing, which decreases the rate at which water leaves the container. So we can construct a slope graph of the depth. Okay, here's our depth graph. We get a nice smooth curve. And we can do tangent lines here, 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 and here. We get 1, 2, 3, 4 slopes. Now all these slopes are negative, so our slope graph is going to have negative values down here. But we can easily construct a slope graph using the same methods that we've always used. Well, of course, we have been using them all our lives, just the last couple of days, but the same methods we've been using to construct slope graphs. Okay, now this slope graph kind of looks like it comes out sort of linear, but it's not real clear. Well, I didn't actually construct this slope graph. I didn't actually construct this curve. I didn't actually use these numbers as a basis for this curve. Okay, so I don't know if that comes out linear or, wobbly or what. But of course, I'm going to ask you to do that and see what you think. Okay, there's another thing, transforming graphs, that's kind of relevant to this graph. And I'm simply going to say, if we take this graph, which kind of has this shape, so we take this shape, and then we reflect this through the y-axis, and then we shift it over so that this point here becomes this point. So we shift over this far, shift every point over this far. We get a graph that looks like this. And then if we shift it down to where this point goes to the origin, we get a graph that looks like this. And we could test this graph to see if it's a power function. Now, in a little later video, we're going to do that in a little bit more detail in case you didn't get it here, because this is just something I mentioned at the very end of class on day 4. But the idea, again, is you just reflect this graph through the y-axis, move it over so this point goes here, move it down so this point goes here. Now you got something that at least plausibly looks like it might be a power function or an exponential function perhaps. If it's not a power function, maybe we move it up a little bit and it becomes an exponential function. So that's something we can speculate on.